Recent scientific discussions suggest that time might not be the fundamental backbone of reality we once thought. Instead, it could be an emergent phenomenon arising from the mysterious world of quantum mechanics. This revelation challenges our deepest intuitions and has profound implications for physics and our understanding of the universe. In this video, we will explore what this means, the science behind it, and why it matters so profoundly. Traditionally, time has been viewed as a constant and ever-flowing river moving uniformly from the past through the present and into the future. In classical physics, time is an absolute backdrop against which events unfold, independent of the observer or the events themselves. This perspective was famously encapsulated by Sir Isaac Newton, who described time as absolute, true, and mathematical, flowing uniformly regardless of external factors. This Newtonian view held sway until the early 20th century, when Albert Einstein introduced his groundbreaking theories of relativity. In his special theory of relativity, Einstein proposed that time is not a universal constant, but is relative, varying with the observer's state of motion. He demonstrated that as an object approaches the speed of light, time for that object slows down relative to a stationary observer, a phenomenon known as time dilation. This was a radical departure from Newtonian mechanics, suggesting that time is intertwined with space, forming a four-dimensional continuum known as space-time. Einstein's general theory of relativity further revolutionized our understanding by showing that gravity is not a force acting at a distance, as Newton had proposed, but a curvature of space-time caused by mass and energy. In this framework, massive objects like planets and stars warp the fabric of space-time, and this curvature dictates the motion of objects and the flow of time. For instance, time runs slightly faster on a mountaintop than at sea level because the strength of Earth's gravitational field decreases with altitude. This effect, though minor, has been confirmed by precise measurements using atomic clocks. These relativistic effects are not just theoretical musings, but have practical implications. GPS satellites orbiting Earth experience both reduced gravity compared to the planet's surface and high velocities relative to an observer on the ground. According to Einstein's theories, the reduced gravity would make the satellite clocks run faster, while their high speed would make the clocks run slower. The net effect is that time on these satellites runs slightly faster than on Earth's surface. If uncorrected, this discrepancy would lead to navigational errors accumulating at a rate of about 10 kilometers per day. To ensure accuracy, GPS systems account for these relativistic time dilations, adjusting the satellite clocks accordingly. Despite these revelations, both Newtonian mechanics and Einstein's relativity treat time as a fundamental dimension. Whether absolute or relative, time is a given, an intrinsic part of the universe's fabric. In quantum mechanics, time is often treated as an external parameter, a backdrop against which the probabilities of different outcomes evolve. This treatment contrasts sharply with the relativistic view, where time is intertwined with space and influenced by gravity. One of the most intriguing phenomena in quantum mechanics is entanglement, where particles become so deeply connected that the state of one instantaneously influences the state of another, regardless of the distance separating them. This spooky action at a distance, as Einstein called it, has been experimentally confirmed and suggests that information can be correlated across vast expanses without any time delay. Such instantaneous connections challenge the classical notion of causality, which relies on a temporal sequence of cause and effect. Recent studies propose that time itself might emerge from quantum entanglement. The Page and Wooters mechanism, introduced in 1983, suggests that for an entangled system, time emerges through the correlation between subsystems. In this framework, one part of the system can act as a clock, and its entanglement with another part gives rise to the perception of time's passage. Without such entanglement, the universe would appear static and unchanging, implying that time is not a fundamental entity, but a manifestation of quantum correlations. This perspective aligns with the Wheeler-DeWitt equation in quantum gravity, which intriguingly omits time altogether. The equation describes the quantum state of the entire universe, suggesting a timeless wave function of the universe. In this view, time emerges only when considering subsystems in relation to each other, reinforcing the idea that time is not a fundamental backdrop, but an emergent property arising from the entanglement and interactions of quantum states. The concept of emergent time challenges the traditional separation between space and time in relativity, and the fixed parameter of time in quantum mechanics. It suggests that a deeper, more fundamental theory might exist, one where space-time and time itself emerge from more basic quantum processes. Such a theory could potentially resolve the long-standing conflicts between the two pillars of modern physics, paving the way for a unified understanding of the cosmos. Understanding time as an emergent phenomenon also opens new avenues in fields like quantum computing and information theory. If time arises from quantum correlations, manipulating these correlations could lead to novel ways of processing information, potentially revolutionizing technology. This notion challenges deeply held beliefs and forces us to confront questions about the nature of reality, causality, and consciousness. Traditionally, reality is seen as a sequence of events unfolding in time, a progression from the past through the present and into the future. However, if time emerges from quantum correlations, then reality might be more like a static block where all moments coexist, and our perception of now is a construct of our minds. This view aligns with Einstein's relativity, which posits that all points in spacetime are equally real, eroding the idea of a universal present. If true, reality itself may not be as dynamic as it feels, but instead, a subjective construct shaped by human perception and interaction with the universe. The concept of emergent time could revolutionize efforts to unify quantum mechanics and general relativity, two of the most successful yet incompatible theories in modern physics. General relativity treats time as a dynamic entity influenced by gravity, while quantum mechanics treats it as an external parameter. Emerging theories like string theory and loop quantum gravity suggest that spacetime, and by extension time itself, may not be fundamental, but arise from deeper quantum structures. For example, string theory proposes that time may emerge from the vibrational patterns of fundamental strings, blending seamlessly with the fabric of spacetime. Loop quantum gravity suggests spacetime is composed of discrete chunks, with time arising from their interactions, while in Wheeler-DeWitt equation, time is absent, implying that the universe can be described in a timeless state, with time emerging only when considering subsystems in relation to each other. These ideas suggest a paradigm shift in physics, where time is no longer a fundamental variable, but an emergent feature of a more profound, unified theory. Time's emergent nature invites intriguing questions about the role of human consciousness in shaping our experience of time. Some theories propose that our brains impose a sense of flow and causalities onto a timeless quantum reality. Neuroscientific studies reveal that the brain organizes sensory inputs to create a coherent narrative of past, present, and future. This mental time travel is crucial for survival, enabling us to anticipate threats and plan for the future. However, if time is an illusion, it raises questions about the relationship between consciousness and the physical world. Could our perception of time be a survival mechanism rather than a reflection of objective reality? And if so, what does this mean for concepts like free will and causality? The implications of emergent time extend beyond physics into philosophy and daily life. Philosophically, it challenges the concept of free will. If all moments in time coexist, as suggested by the block universe model, then our choices might be predetermined, with the sense of freedom merely an illusion. Thank you for watching. We hope you enjoyed this exploration into the fascinating concept of time as an emergent phenomenon. If you found this video insightful, don't forget to like, subscribe, and share your thoughts in the comments below. Stay curious, and we'll see you next time for more captivating discussions on science and the mysteries of the universe.
I'm doing this video on time travel. I want to give my explanation of what's happening with the essence of Albert Einstein's ideas of time travel. My video starts out with explaining that to Einstein everything was relative. If you put it in that perspective, everything is connected to everything else. The planets are connected to other planets. This goes into like Newton's theory, except in Newton's theory, everything they repel because they're similar matters. So all the planets in the relative Einstein theory are connected. The solar system's connected to the other stars in the galaxy, and so forth. The galaxies are connected to each other in the galaxies, in the universe. Now you take this and his ideas about time travel, or what people perceive to be time travel, that he talks about in special relativity. With that in mind, he launches a ship in space. Coming close to the speed of light, everything seems to shrink behind him. As he gets closer to the speed of light, time in his ship becomes less than time, regular local time with the planets and stars. So his ship drags, if everything's connected, his ship drags the planets and makes them turn. And since the planets and stars are rotating backwards in the universe, they slow their rotation and they eventually stop, but they start slowing down. That's his theory. To make it simple, his ship is a magnet, and it's more powerful than all the relative stars, planets, and galaxies. And that's his time travel. Everything is relative. Now, to go into it a little further, we have, or he has in relativity, slow dragging, which I just explained. When the ship, the faster it goes, the slower the planets rotate. The slower the solar system orbits. They slow down. So in essence, time slows down in relativity. I don't know how many scientists believe this to be a factual truth, but it's classical physics. It's there. The reality is, if you look at reading some of my videos, I'm always talking about the reality of relativity, or the unreality of relativity. There's no connection between a moving ship and the planets. No matter how fast you go. Is there a speed limit? A universal speed limit, which Einstein collectively says is the speed of light. The speed of light was chosen because, as a measurement, because it has no mass. And if it has no mass, there's no connecting energies that would cause it to slow down. Now, it's made that way. But everything else has energy and is affected by everything else except light. So light is his universal constant. But what I think he neglected to realize is that's only light. He said it himself. Everything else has energy, which is affected by everything else that exists. And the only other element that exists with a zero mass is space. Space itself has a zero mass. There's no detection in midfield space. Newton's theory shows this as similar masses repelling each other, like a positive pole and a positive pole. They don't attract. One has to be positive and one has to be negative. So all matter is made up of some sort of positive energy. Now, at one time, I think he wanted to connect this with electricity, but I've been studying this stuff for like 15, 20 years, and actually relativity, and I don't know what his exact statements are about that. But in reality, everything is relative but light. Our ship is made of positive matter, but our ship is traveling in empty space. And the space that Einstein talks about is gravity. His theory on gravity, that space is flat. That's space gravity now. Or the universe is flat, and it has a surface. It's made up of a fabric, and like a boat, it travels around on top of this fabric. But a planet gravity is energy. It's the effect of moving objects that aren't tied down by like a mountain or something, or a rock on a mountain. They're tied down. And we have a gravity force that when something is in motion, it is affected by gravity, which makes it fall back to the ground. But it makes it have the ability to leave the ground behind a force, like jumping. You jump up and you come back down. Even on the moon, you jump up, but the only thing about the moon is you go around 15 feet before you come back down, and the difference is about 8 point meters a second, if you want to put it that way. So Earth gravity is what, 11? It equals 11 or 9.8 meters a second. Meters a second, where the moon is like 2 meters a second, which means that we have the other 98% ability to have momentum as we are moving vessels, or like a car. We jump, people jump, airplane. But when you get in space, it's different. It's so big. It's not a surface. It's three-dimensional. We are inside of it. And we float. Einstein's idea that we float is the universe itself. The idea that like early in the early universe, everything was hot and molded, and primary to its cooling off, elusive matter was created and it floated to the top, and that's where the surface is. That's Einstein's idea. But I don't think it worked that way, or it works that way. And if you look at some of my videos, I got a lot of good videos on what's called space expanse gravity, or expanse vacuum gravity. I have a lot of videos on it, and it explains space and the flowing of time and the separation between space and time. Now, Einstein says they're both preserved together and everything is relative. But what that means is that's based on the speed of light, which he says is constant. It's not constant. The universe is not constant. In 1925, or when Hubble discovered, it was expanding. It was getting bigger and bigger. So there's room for velocity for a ship to travel faster than the speed of light. In Einstein's theory, a ship seems to have the ability to slow down all the planets as it goes through space. Do you understand that? Anyways, I'll give a good explanation of space expanse, not universe expanse. Universe expanse is different. It's the idea that the galaxies are moving away from each other due to some kind of force. The force that creates the mobility of all the galaxies and all the planets involved inside these galaxies is the Hubble balloon, or sphere. I call it a sphere. That seems to be getting bigger and accelerating the space around it. See, the space around this sphere is like a river and going through all the galaxies and sinking inside the galaxies and making all the planets in there spin as well. You know, it's the force of his anomaly that is expanding. And my ideas and theory, it's the same thing, but it's space that is creating mobility of all the stars and things. We can call it motion. And that's what gives everything momentum. That spin. We can't feel it, but the Earth is rotating, you know. And by the second, it's measured by 18.6 miles a second, you know, until it makes in one day one revolution. Or one day. Anyways, This is what happens when you do a lot of research. You gotta go back and think things out, which is not, Anyways, that's Einstein's perspective about time. And light seems to be the key element. They're trying to make negative energy. See, when matter energy is excited, it can be excited with light. And when it's excited with light, it gives off a negative energy. And if you're in a ship and you can make the ship somehow reflect light and create this excitation, you would have negative energy, which means that it's like anti-gravity. On Earth, it would be anti-gravity. In space, it means you wouldn't be affected by anything in the same way the light is. You have zero mass. Now, that's their ideas, but see, space already has zero mass. It isn't a mass, it's some sort of element. And so a ship traveling that can press a button and generate enough light, let's say, to excite all the molecules of the ship and create a negative flow of energy, which is in the Alcapre warp drive theory, it would probably have no limit of velocity. So they say. But to do that is something else, It's like bending space. Now, Superman could bend steel with his bare hands, but I don't think you can bend space. You can't even. Space is a vacuum. How can you grab hold of it and you can't even touch it? It's just there. And it's 0 point, which means it's already reached that point of no segregation. So, in evidence, space is pushed with a repulsive force, causing it to make the galaxies all around it, billions and billions of galaxies, maintain a path. And they're different sizes, and so they rotate in different time frames. But according to Einstein, the time frame is the same everywhere, and it's just the opposite where the planets are different sizes, and they do maintain different time frames. Kind of contradicting that. But anyways, a lot is said. I don't know why Einstein went into past and future type space travel fairy tales. They're like fairy tales. It's like making a child understand what you're talking about when you're talking about something that is very complicated, and then you would say, well, it's like making a cake. Oh, okay, yeah. But anyways, in essence, his GRT, his theory, I think he was small in mathematics. He didn't know a lot of mathematics. E equals mc squared came from P equals mc squared, which was formerly named properties, and I don't actually use it, but P in propulsion, in the same way that Einstein put equals m squared, or E equals mc squared. He also made another equation, E equals mv squared, which means velocity. But he never talked about velocity, except for the speed of light, which he claimed to be constant. Nothing can go faster than the speed of light. Like I just explained, the repulsive push force of the universe itself, the one that pushing galaxies. See, all the planets and stars and solar systems are inside these galaxies. That's where we live, in this galaxy called the Milky Way. And the repulsive force is what keeps us moving. The stars, the galaxies rotating, moving, because like a river, this anomaly that we reside outside the surface of this anomaly is pushing everything and creating a flow of space that makes us orbit, makes everything, the galaxies most, put them in mobility, make them rotate, have an orbit. And it expands at a constant. And because there's momentum, which is another thing that relativity doesn't talk about, where Einstein said everything's relative and acts on everything else, and the speed of light is the limit, and it's constant. Since we have mobility in the galaxies, we are moving faster than the speed of light. Nothing can travel. Imagine everything in a bubble universe, all moving at the same specific rate. Nothing changes. Some are small, some are big, and they move a little faster and a little slower and stuff like that. And you have a limit for the speed of light, what you call the universal constant, or Einstein called the universal constant. So anything that's going to upset that is showing proof that in expansion, that push force that is changing things, that's the evidence. That the idea that you put two galaxies together, or 10 of them, and you measure in between two of them, they're moving away from each other, which is a repulsive type force, and only at 43 miles a second. That doesn't seem like a lot, but you take that 43 miles a second relative to the speed of light, Einstein's format, you have a lot of energy or pressure that is manipulating space. It can't just be light. It has to be a physical property, and light is not a physical property because it has no mass. You can see it. You know where it comes from, but it has no mass. And the vacuum has no mass. So any interruption would be expanse, which is faster than light. And if you can correlate the pressure, then you have a new speed limit. It correlates with how much force is creating the expansion. The same way Einstein took the speed of light and said it's the fastest thing we know that exists. And that's classical physics. Some people call it modern physics, but it's classical. Anyways, I wanted to explain a little bit about that, it's not that Einstein, they thought it was the greatest thing in the world, but only 5 people in the whole world actually comprehended what he was talking about, could comprehend his scientific theory. And it took me a long time to start figuring some of this out. It's kind of simple towards the end. And then I went and looked at the Hubble universe expanse and correlated a greater speed limit, 450,000 miles seconds approximately. And the only thing is, as this anomaly gets greater and greater, that force changes. That's why we have what's called the runaway universe. It's continually at a constant, creating more pressure in the universe. And when we look out into the vacuum of empty space, past the anomaly surface and all the galaxies that surround it like a beehive, how much space is out there and how much push or how big this anomaly gets predicts and explains the reality of our universe. And I don't think we'll ever go there because we can't measure it, much less see it or what it's made of. But I did write a book that shows that the aspects. See, a lot of people think we live in a black hole and everything is stuck in this black hole, and we're stuck at the speed of light, and we're in a bubble inside a black hole. But like I said, in expanse theory, the galaxy is set outside this Hubble balloon, this anomaly, and we sit outside black holes that we have evidence of. We are outside and we're not inside, and we're outside of them. So I did write a book on that. The universe should have a vortex, but does not. The universe should have a black hole, but it doesn't. We have an anomaly, and if you go back into the beginning, point zero or time equals zero, how this anomaly was formed, I give an explanation. Whether it's true or not, I don't know. But the way things are going and the way we seem to preserve our knowledge about our universe, it's probable. So, I want to get out this video. My name is Rod Kowicki. Check out my books. I got a lot of them. Amazon, I guess. Yeah, Amazon. I'm going to come out with a big one, about 500 pages, 600 pages in the near future. My name is Rod Kowicki. Thank you. Hello, my name is Rod Kowicki. I'm doing this video on physics, mathematics. I'm developing a new theory on physics. I've done about 15 years of study and everything. A lot of things keeps coming up. Relativity seems to be the accepted theory. When anybody wants to talk about physics, they talk about relativity. Relativity has a lot of flaws, I hate to say. And I'm going to tell you about one in this video. My name is Rod Kowicki. Thank you.